So the next recap is going to be on analysis. Okay. Now, why do we need to worry about analysis in the first place is because we, in any optimization algorithm, we are concerned about convergence. Supposing I have an algorithm that is trying to give me an optimum solution, I'll have some starting point and some end point, right? Before I go about coding up the algorithm and deploying it, I should have some confidence that this is going to work. Now, how do I quantify does it work? I'm going to use tools from analysis which will quantify convergence. Does it converge? That's itself a big question. Many people use algorithms, optimization algorithms in the research world, in industry also, which actually do not have a proof of convergence. Convergence is a difficult property to prove, but when it does work, then it gives us a lot of confidence. Okay, so that is why convergence is an important property. The other thing is, again, a very practical matter. I may give you an algorithm that converges, but if the rate of convergence is very slow, it may not be practical. And you will come across these kind of situations where a researcher has coded up an algorithm, has a proof of convergence, they're very happy about it, they're solving the problem, but they find out that, the solution is just not, it's not, you're not getting it in the time that you've given. And then you do an analysis, you find out that the rate of convergence is so slow that it would take 2 years for the algorithm to converge. So isn't it better for you to know that before you hit enter on your simulation, right? So these are two important things that we want to know. Does it converge or not, and the rate of convergence. So there are tools from analysis which help us to quantify this. Okay. So existence, right? That's another, I mean, it's kind of related to convergence. Does it converge at all is related to, does there exist a solution? Does there exist a point at which the sequence converges? So these are related. These are not always easy to prove. Okay. So where possible, we will study them. Okay. So how will I denote a sequence? So we are all familiar with sequence of scalars. For example, I give you the sequence 1 over n, right? That's 1, 1 by 2, 1 by 3. That's a sequence, but it's a scalar sequence. But we know that most engineering problems are going to be specified in some n-dimensional space. So I need to talk about sequence of vectors, not sequence of scalars. So sequence of vectors okay, I'm going to use the notation which I developed earlier. Okay, so you can say xi in curly brackets is a sequence of okay. If you get confused by this idea, just think of an algorithm that is starting from some initial point and going to some intermediate point. And as the algorithm is going from these points, at each point your x is an n-dimensional vector. I'm starting from somewhere and I'm going to somewhere, so I get a sequence of points. Let's say every iteration gives me 1x. So now I've got a sequence of points. So this will help you to have a geometric picture in mind of what I mean by a sequence. Okay. So now let's talk about convergence. Okay. The definition of convergence is very intuitive. Okay, so let's just write that down. Okay, so a sequence is said to converge to a point x. Okay, how do I denote this? Simply by saying that limit as k tends to infinity of xk is x. Okay. But more formally, what do I mean, right? So it means that if for any epsilon greater than 0, okay, there is an index k. Index just means you can just take a number k. Okay, so this is the definition of convergence. So what is it saying? Let's not get bogged down by the mathematical definition of here. Let's interpret this in plain English. What is this saying? So there is a norm over here, not absolute value, because I'm talking about vectors. How do I geometrically interpret this quantity? Xk minus x norm means what? Not neighborhood, distance. Plain English, this is distance between the point xk. Can I call xk a point? Yes, it's a point in n-dimensional space. So xk is a point, x is a point at which this sequence is supposed to converge. And what am I saying? Xk minus x, the distance between these points. And as k begins to increase, as the sequence number increases, what am I saying? Now let's bring in the inequality over here. Less than epsilon means I can choose for any epsilon greater than 0. That means I can choose epsilon to be as small as I want. Right? So what is it saying? That as the sequence grows, the distance of the sequence point to its convergent point reduces. It's very intuitive, right? I mean, when I say a sequence convergence, that's what you have in mind. That as I approach, as the sequence grows, I get closer and closer to the point of convergence. So in English, it's very easy to understand. If I draw geometrically, it's very easy to understand. But just the language of formalism sometimes may seem intimidating, but you can see this is a very simple definition. Okay. So this is a simple definition of just convergence. Okay. Which norm? Okay, good question. Usually if I don't write anything over here, it means I'm using the 2 norm. Okay. So this is kind of implicit over here. But there are many results in analysis where if you prove a result for one norm, it holds for other norms also with some constant factor getting multiplied, right? So it's often it is enough for you to prove the result for one norm and other norms then follow. So you pick the norm in which math is easiest. Okay. So this is about just convergence of a sequence. Then there is, you know, a little bit more fine tuning of types of convergence. Okay, so we are going to look at a special type of sequence, okay, which is called a Cauchy sequence. So a sequence is called a Cauchy sequence. Okay, so if again there's going to be our epsilon greater than 0, okay, if for epsilon greater than 0 there exists an index, or let's say an integer k, okay, such that the distance between xk and xl is less than epsilon for all k and l greater than capital K. This is capital K. Okay. So this is called a Cauchy sequence. Again, in geometry, it's very easy to understand that once I go past a certain threshold, then the distance between any 2 points, it begins to get smaller and smaller. Okay. So this seems like a little bit more specialized kind of a sequence. And the reason I mention it is because in some of the proofs of the algorithm, such a sequence comes. So it's just good for you to know the definition. We're not going to do anything with it. I'm not proving anything over here. I'm just putting this over here so that when you read research papers for your course project or for whatever, you come across this, you don't kind of freak out, right? So this is just a Cauchy sequence. Okay. All right. So having sort of scared you a little bit with vectors, sequences of vectors, we'll fall back to scalar sequences where you are much more comfortable, right? So scalar sequences. Okay. Simple notation again will be something like Tk, and in this case it belongs to R. Okay. So you all are familiar with a sequence being bounded from above, bounded from below, right? So okay, I need not mention that in great detail. Okay, let's talk about one thing which sometimes can get confusing. Okay. So I'll give you an example so that when you see the example, you'll follow along in a much more easy way. So I'm going to define a function f, which is sin x by x, which should be familiar to all of you, right? But I'm going to play a little bit of a trick over here. Sin x over x, is it defined for all x? No. Where is it not defined? It's not defined. Does sin x over x not exist at x equal to 0? It's defined, right? There's no singularity, there's no Dirac delta function here. It exists in the limit it exists. But what I'm going to do is I'm going to say x not equal to 0. Okay. I'm creating this artificial example just to explain a few definitions that will happen. So if I plot this graph, what will I see? Something like this, right? This is f. But this point over here is not allowed. So if I ask you what is the set of all possible values that f can take, that is what I am talking about. X is the entire real line minus 0, no problem. Now there is also a set of values that f can take, right? Now f can, to look at f, I have to look at the y-axis of this plot. Clearly, for example, f is never going to reach minus 1, right? Is f going to ever reach 1? F will also not reach 1, right? So let's look at the set S of all the possible values that this function can take. Now, keeping this in mind, I'm going to define something very general. You can look back at this and see, right? So let S be a non-empty. This is how they write it. Okay. What does that mean? That S, for example, S is the set of all values that f can take. Non-empty subset of R means is some subset of R which has some stuff in it. It's not empty. That's all. Okay. Let's talk about the upper bound of this set. Okay. It's going to be U, okay, belonging to R, such that x is less than or equal to U for what? For all x belonging to S. Okay. Actually, just to make life a little less confusing, I'm going to call this Y, okay. Same thing. This is the definition of the upper bound of a set. It's very intuitive. Find a number such that every number of the set is less than that. Fine, right? But notice I have not made any restriction on U. U can be anything. So for example, is 5 an upper bound for the set S? The number 5. It is. Because any possible value of f that you can see is going to be less than 5. So no problem over there. So it is an upper bound, right? So that's the definition of upper bound. There is no restriction on the upper bound belonging to the set itself. Okay, that's what I want to. That's why I've picked this artificial example. Okay. The next is, amongst all upper bounds, is there a special upper bound? There's something called the least upper bound. Another word for least upper bound? Supremum. Right? Does it always exist? I mean, forget this example. Does it always exist? It may not exist in general. So we'll say if it exists. For example, if I have a set where the numbers are going to infinity, then there may not be any supremum. Okay. Right, so the supremum is simply the least upper bound, okay. And then C, now here is where I will make a little bit of a special case. If the upper bound belongs to S itself, then what do we call it? We call it the maximum. Yeah. Okay. So these are the kind of 3 different definitions that you can keep in mind, which you will see being used in the papers and textbooks. So when you read this now, you know precisely what it means. So if I ask you, for example, what is the supremum of this example that I took? Supremum is 1 because it is the least upper bound, right? I cannot go lower than that. It is the least upper bound. If I ask you what is the maximum of this set S, it is not 1 because there is no x for which f takes the value 1, right? So this set does not have a maximum, but it has a supremum, right? So if I had given you these definitions without the example, it would have been very confusing. But with this example, it's perfectly clear, right? Whether the only distinction is whether the upper bound belongs to the set or not. That's all. Okay. But I mean, this is often something that mathematicians care a lot about. Engineers are like, okay, let's just put it to use, get our result. Okay. So this is about sequences, right? So this is, so we started by talking about convergence of sequence, then we're talking about, you know, supremum. Correspondingly, I can talk about the other side also, which is what? Infimum and greatest lower bound, right? So I'm not going to repeat that, it's quite intuitive, right? So we can talk about that as well. Then the thing that we will, you know, use a lot in this course is the rate of convergence, because rate of convergence will make a difference between your simulation converging before you graduate or not, right? So that's why we want to study this little bit carefully. So convergence. And I'll tell you, this convergence issue, it's very important to understand, because if you don't understand it, I mean, from my own research experience, I can tell you there was a student who wrote an algorithm and was very proud and confident of the fact that this is going to work and give the solution. But we did a back of the envelope calculation, and which showed that it will give an answer in approximately 3 times the age of the universe. He had not done that calculation. He had set his cluster to solve this huge thing on MATLAB, right? But you know, if you did that calculation beforehand, you would realize that I should do something different, right? So that's why this is important to know. Okay, so how do we quantify, right? So how to quantify? Okay, so the word Q will be used over here, which is simply stands for quotient. It will become clear what I mean. So the first rate of convergence is something which is called Q linear. So in simple language, people will say linear rate of convergence, which simply means that xk plus 1 minus x star. X star is denoting the point to which the sequence converges, okay, divided by xk minus x star. What do you think? Should this number be greater than 1 or less than 1, or ideally what would you like it to be? Less than 1, right? If it's converging, it had better, the distance had better get lesser and lesser, right? So if I define this as R equal to all, okay, sorry, for all k, let's say for all large k, and R belongs to 0, 1. Okay. So this ratio is some number less than 1. Obviously greater than 0 because all norms are positive quantities. Okay. If your sequence satisfies this, you will say that I have linear rate of convergence or Q linear. Okay. The next is something called superlinear, Q superlinear. We do not know x star beforehand for any. If we knew x star beforehand for any sequence, then we have already solved the problem. Okay. So this for you to evaluate this, in many algorithms, you need not actually know x star. You need to just know how is the difference growing. It will become more clear when we actually take the first algorithm that we take. We will analyze its rate of convergence, and then this will become clear. Okay. Yeah, that's actually, it's a good point that he mentions. Many of the mathematical proofs assume that I know the convergence point x star. So from a practical engineering point of view, it becomes a very funny thing that if I already know the point of convergence, the story is over. Why am I doing this, right? But right. So okay. So coming to this superlinear rate of convergence, this is similar to the above, except I'm going to take the ratio of the norms in the limit as this goes to infinity is actually 0. If a sequence satisfies this, then I'm going to say that this sequence has superlinear convergence. And the third and final rate of convergence that we will talk about is Q quadratic. Okay. Q quadratic, as you can imagine, the word quadratic means there is some term is going to get squared, and that square term is actually going into the denominator. So this is xk plus 1 minus x star, xk minus x star squared, okay, is less than m. And the only restriction on m is that m greater than 0. M need not be even less than 1. This is all there is. Okay. And turns out that you can imagine I can come up with all sorts of funny definitions, right? Instead of square, I can say to the power 1.75 or whatever, right? But it turns out that most algorithms that we have, they fall into one of these three categories, which is why we have defined these three categories. Okay.